When using the DFT, or the inverse DFT, we have to make a choice for the number of samples n that we will use. In this video we will explain which implications the choice of the length n of the DFT will have for different types of signals. But let's first repeat the main equations. The DFT transforms n samples of the discrete time signal xn into n discrete samples xk, which represent a frequency domain representation of signal xn. The DFT frequency index k is related to the relative frequency index theta as k times 2 pi divided by n. In other words, the n frequency domain DFT samples xk represent n equidistant samples of one fundamental interval. As a result of the main rule of thumb, sampling in one domain results in repetition in the other domain, we've seen in a previous video that both time domain and frequency domain representations are periodic sequences denoted as xpn in time domain and xpk in frequency domain, respectively. The index of these periodic extended signals can be described by using the modulo n operator as denoted in the equations. Only one interval of n unique samples will be used. In most cases, this is the interval which ranges from 0 until n-1. In practice, the signal samples xn can be the result of sampling a signal which is periodic, non-periodic, finite or infinite duration. In the following slides we will explain the consequences of choosing the DFT length n of each of these signal types. In case the number of samples of signals xn is limited to m samples, the infinite summation of the FTD equation reduces to the given finite summation, in which the relative frequency is represented by the continuous variable theta. The endpoint DFT summation reduces to a summation over m samples in case the DFT length n is larger or equal than m. The DFT frequency index within one fundamental interval ranges from k is 0 until k is n-1. When comparing the FTD and endpoint DFT equations for such a finite length signal xn, it follows that the n DFT samples xk represent the sampled version of the FTD in which the n equidistant samples have an intersample distance of 2 pi divided by n. The following slide will show some examples. The first example is a signal which consists of m is 8 samples as depicted in the figure at the left hand side. The FTD result is depicted at the right hand side, in which the relative frequency theta ranges from 0 to 2 pi. When applying an 8-point DFT, we clearly see at the right hand side that the 8 DFT samples xk are sampled versions of the FTD. The inter-frequency sample distance is 2 pi divided by 8. Increasing the signal length xn with the zeros, which is called zero padding, does not influence the FTD plot, as shown on the slide. On the other hand, when applying a 16-point DFT to the zero padded signal results in 16 DFT samples xk, which represent sampled versions of the FTD with an inter-frequency sampling distance of 2 pi divided by 16. From this result it follows that zero padding, or using a larger DFT length than the signal length, leads to a finer grid of the resulting DFT frequency samples of the underlying FTD plot. For periodic signals, it may seem obvious to choose the DFT length n the same as the number of samples of one or more periods. In practice, however, this is not always trivial. By the following examples, we will show the result of such a mismatch. The plot at the left-hand side shows the 6 samples of one period of the periodic signal xn is cosine 2 pi divided by 6n. The plot at the right-hand side shows the result of a 6-point DFT in which we see two frequency peaks at indices k is 1 and k is 5. Via modulo counting, it follows that the index k is 5 is equivalent to the index k is 5 minus 6 is minus 1 in this case. Furthermore, the interfrequency distance of the 6-point DFT is 2 pi divided by 6, which implies that the two frequency indices k is 1 and minus 1 are related to the relative frequency theta is 1 times 2 pi divided by 6 and minus 1 times 2 pi divided by 6, which are indeed the two phasor frequencies of the sinusoidal signal xn. Now we use 2 times 6 is 12 samples of xn. The result of a 12-point DFT shows again two peaks, but now at indices k is 2 and k is 10. Via modulo counting, it follows that the index k is 10 is equivalent to the index k is 10 minus 12 is minus 2. Furthermore, the interfrequency distance of the 12-point DFT is 2 pi divided by 12, which implies that the two frequency indices k is 2 and minus 2 are related to the two relative frequencies theta is 2 times 2 pi divided by 12 is 2 pi divided by 6 and minus 2 pi divided by 6, which are indeed the two phasor frequencies of the sinusoidal signal xn. However, when using n as 16 samples, which is not a sixfold, the 16-point DFT result shows two peaks that are smeared out. In the following slides, we will give three different explanations for this phenomenon. Each of these explanations will lead to another and better insight of the DFT operation. The first explanation is a mathematical one, the second a more physical one, and the third is a mix of these two. In the first explanation, we use the twiddle factor property, which has been discussed in a previous video. This property implies that when summing, capital letter, n twiddle factors of e to the power plus or minus j 2 pi divided by capital letter n, up to a power of frequency index k, the result is always 0 except for k is 0 or an n-fold. Furthermore, it's important to realize that all indices in this equation are integer numbers. First, we use this twiddle factor property for the evaluation of the 12-point DFT of the same sinusoidal signal xn as on the previous slide. In the first step, we use Euler to write the sinusoidal signal as a sum of two phasors. Then we combine the complex exponents, which lead to a summation of two twiddle factor property results. The first summation is always 0, except for the case when the frequency index 2 minus k modulo 12 is equal to 0. Thus within the fundamental interval, the first summation is equal to 0 for all frequency indices k, except for k is 2. The second summation is always 0, except for the case when the frequency index 2 plus k modulo 12 is equal to 0. Thus, within the fundamental interval, the second summation is equal to 0 for all frequency indices k, except for k is minus 2 plus 12 is 10. Concluding, it follows that the 12-point DFT of the periodic sinusoidal signal xn is cosine 2 pi divided by 6n, results into two peaks at frequency indices k is 2 and k is 10 respectively, which is indeed the same result as a 12-point DFT plot as shown on the previous slide. Applying similar steps for the evaluation of a 16-point DFT of the same periodic signal xn is cosine 2 pi divided by 6n results into the following steps. However, when trying to apply the twiddle factor property, it follows that in the first summation the frequency index k has to be equal to 16 divided by 6, which is not an integer value. In other words, the twiddle factors of the first summation will add up to a non-zero value for all frequency indices k. A similar reasoning follows for the second summation. This implies that the 16-point DFT result of the sinusoidal signal xn is cosine 2 pi divided by 6n results in two peaks that are smeared out around integer indices k, which are close to the values 2.7 and 13.3, which is shown in the 16-point DFT plot of one of the previous slides. A second, more physical explanation is as follows. When applying a 6-point DFT to the sinusoidal signal xn is cosine 2 pi divided by 6n, we use 6 samples, colored in red, which span exactly one period of xn. We've seen before that the DFT frequency samples represent the frequency content of a periodic extended signal. In this case, the 6-point periodic extended signal is shown in the figure. Because of the fact that one period of xn consists exactly of 6 samples, in red, the samples of the periodic extended signal are exactly the same as the samples of the original periodic signal xn. In other words, the peaks of the DFT frequency samples coincide exactly with the peaks of the phasor frequency of xn in this example. The same reasoning holds when choosing the length of the DFT any other 6-fold, thus n is 12 or 18, etc. On the other hand, when using a 16-point DFT, or another non-6-fold in this case, the periodic extension will cause artifacts at the edges, since 16 samples do not fit in an integer amount times 6. As a result, the peaks of the DFT frequency samples do not coincide with the peaks of the phasor frequencies of xn in this example. So we can conclude that the smearing out effect is caused by the mismatch of the periodic extension. From this reasoning, it follows that the smearing out effect can be reduced by minimizing the artifacts at the edges. This can be done by multiplying the original n signal samples with a so-called window function. The shape of such a window function is typically close to 1 in the middle of the segment of n samples and close to 0 at the edges. An example is the Henning window. At the left-hand side of the plot we see, in red, the n is 16 windowed signal samples of the periodic signal xn is cosine 2 pi divided by 6n. At the right-hand side we see in black the original DFT result, thus without windowing, and the DFT result with windowing is shown in red. From this we can see that the smearing out behavior, especially in the range of frequency indices k is 5 until k is 11, is reduced. For the third explanation of the smearing out effect, we will step through all intermediate steps when evaluating the DFT of a sinusoidal signal with a relative frequency theta is 0.28 pi. The FTD takes into account all samples of the infinite long periodic signal xn, which results in 2 delta pulses, as depicted in the figure. These delta pulses, which represent the phasors of the sinusoidal signal, are mathematically defined functions which cannot be measured as such in practice. In practice, we can only measure a part of the signal. This can be represented by a multiplication of the infinite long original signal xn with a finite length rectangular window function wn. In a previous video we've seen that the FTD of a rectangular function results in a so-called Dirichlet function. This is a function which looks like a sinc function. Its main lobe width is inversely proportional to the window length. Thus, the longer the window length, the smaller the main lobe width. Furthermore, as a general rule of thumb, we've seen in a previous video that multiplication in time domain results in convolution in frequency domain. As a result, the FTD of the finite length windowed signal x-win with n is 32 is depicted in blue. The delta pulses are smeared out by the shape of the Dirichlet function. When applying a ns32 point DFT to this finite length signal x-win, the result is a sampled version of the FTD of x-win, from which the interfrequency sampling distance is equal to 2 pi divided by 32. This DFT result is depicted by the green spots. From this result, we can see that depending on the relative frequency of the original signal xn and on the choice of the length n, the DFT samples may or may not match exactly with the original phasor frequency peaks. By applying zero padding, in this case up to a length of 4n, and calculating the 4n point DFT, the result, depicted in red spots, is a sampled version of the FTD of x-win, from which the interfrequency sampling distance has decreased to 2 pi divided by 128. The underlying FTD of the length n windowed signal x-win is sampled with a finer grid, and the position of the phasor peaks is shown more accurate by the DFT result. Finally, it's important to note that by increasing the zero padding more and more, that is, using a DFT which is much larger than the n samples of x-win n, we can only make the sampling grid of the underlying FTD result of x-win finer and finer. However, the main lobe width of the underlying Dirichlet function, colored in blue, cannot be reduced by zero padding. The smearing out behavior can only be reduced by increasing the window length n, thus taking more samples of the original signal xn into account. In this final example, we will show that the endpoint DFT of an infinite length signal will always be an approximation. In this example, we use the infinite length signal xn as depicted in the figure, which is an exponential decaying function which starts at index n is 0. The FTD of this function results in an infinite sum from which the exponents can be combined, which reduces into the given mathematical result. A plot of the absolute value of this FTD result is depicted in the right-hand side figure, which clearly shows the low frequency behavior of the exponential decaying function. When applying a DFT of length n is 3, we use the first 3 samples of xn, that is, samples 0, 1 and 2, which results in 3 DFT coefficients with an interfrequency sample distance of 2 pi divided by 3, which are shown in red in the right-hand side figure. From these samples, we clearly see that the samples are not exactly the same as the sampled version of the FTD result. The main reason is the periodic extended behavior of the DFT operation. The 3 resulting DFT samples represent the frequency content of the first 3 samples of xn, which has been periodic extended, as shown in the left-hand side of the figure. From this, we can clearly see the mismatch between the original signal samples xn and the periodic extended signal. It's obvious that, in this case, we can improve the result by using more samples of signal xn, that is, increasing the length n of the DFT. In the plots at the bottom of the slide, the DFT length n is increased to n is 6. However, in general, the DFT will always be an approximation of the FTD when the signal has infinite length. This ends this video in which we discussed the implications of the choice of the length n of a DFT for different types of signals. Thank you for your attention.